right here we've got a Fresnel lens. If you check it out, it's a flat piece of acrylic. So most lenses that you see, they're either concave or convex. So these words might be a little bit strange, but concave means that the lens bows inward towards itself like this. Convex lenses are more like the magnifying lenses you might see in a magnifying glass. They bow outwards, so they're rounded. This one is flat. Now, it focuses the sunlight still, just because of all these tiny, tiny little grooves that are cut in it, all circles around a central point. So all those little circles bend the incoming light to a single point called the focus of the lens. So the focus of this lens, we have it positioned so that it's going to be just above where this can is. And I'll show you where the focus is in a little bit with a piece of board that I'll light on fire for you. Now, when we focus the lens by turning it into the sunlight so that the sun is normal to the plane, it's going to be very, very bright. So the camera can look at it, but we'll have to wear eye protection. So when we don't want to be burning things with this or collecting sunlight at all, we want to face it so that the lens is parallel to the incident sunlight. That way the shadow that it casts is going to be right in line, about the width of the 2x4 that's framing this. Otherwise, we're going to be focusing it and we don't want to burn things inadvertently. Now, a little bit of math quick. We've got 4 foot height, 3 foot width, so it's approximately 12 square feet of lens that will be focusing down to a square inch focal point. So 12 square feet, 144 square inches per square foot, so we're looking at 1,728 times the power of the sunlight landing on you at any given moment, landing there. So instead of focusing a nice inch of sunlight on an inch of concrete, we're focusing 1,728 square inches of sunlight onto 1 square inch of concrete, which means we can melt it into glass because the concrete is just made out of sand and other elements which will come together, fuse up silicon dioxide, make glass. Cool. So now again I've got the lens pointed so that the sun is coming right through it, refracting all toward that central focal point. Now, it's a soft focus on that platform down there, so it's not going to burn anything right away, although it's still very powerful there, and you do not want to put any body parts in there, hands, feet, whatever. I'm going to put on my goggles because I can't look directly at the focal point, although the camera is capable of doing that. And then I've got this piece of board right here, and I want to show how quickly the sun's energy, when it impacts on this, is going to set this aflame, past the combustion point, and ignite it. So I find where it's hitting the light, and then I bring it up to the focus. And you can very clearly see that if you hold this in the focus, it's on fire quite rapidly. And if I can trace it along through the focal point here, get a nice clean focus on it, it will scorch almost instantly as it passes through. Now, yes, this is very, very fun for lighting things on fire. That's all well and good. But what kind of practical applications do solar collectors serve? Well, right here, this kind of a lens could be used for cooking outdoors very, very efficiently. If you don't focus the lens immediately on that very, very tiny dot focal point, but instead you have a softer focus so that the area, all the sunlight coming in is spread to a larger area, say maybe 1 square foot, then it's just a 12-to-1 concentration, which is going to allow you to cook things in cast iron or other high temperature media. So you could do a lot of cooking in this, which would be completely petroleum byproduct free aside from manufacturing the lens, but you don't need to supply electricity to a stove that comes from burning fossil fuels. You don't need to burn propane or anything else to provide the heat. So these are very, very good for developing nations that don't have the infrastructure to allow for cooking to be done elsewhere, which is very nice. It's gonna be a bright, bright, sunshiny day. All right, so right now, we're melting some sand. Sand is silicon dioxide, SiO2. That is the same compound that makes glass, and I think quartz. So when we heat the sand up enough, it loses all of those grain boundaries and it all fuses together, it melts together and forms glass. So if you get nice and closer, you can see where it's starting to fuse and form a solid layer of molten glass, which is really, really cool. There is a guy who has taken a large Fresnel lens and made a 3D printer using sand to manufacture glass objects. It's really cool. There's a link embedded in this video. But have a look at that. I'm going to take the focus off and you'll be able to see the color that the sand is without all that intense sunlight on it. Oh, it's so cool. It's really actually so hot. Check this out. Yeah. Wicked hot. Glass. Haha. Glass. Forged by the sun's heat. Science. The lower cost alternative to the refracting solar collectors like lenses would be reflective type solar collectors. So we have parabolic mirrors. Parabolas, you probably heard about them in mathematics class, but they have a focus as well. So the rays of sunlight coming in are going to bounce off of the reflective surface and all bounce to a central focal point. Now you'll notice that the sun is over there and I'm pointing this away from the sun while I'm doing this demonstration, because if it were pointed into the sun and I brought my hand up to the focal point, it would be burned, which is a bad idea. Now, if you can't make a pure parabolic reflector like this dish, you can always put together faceted reflectors like this out of any shiny surface. So one of the great things about these reflectors is that they can be made out of scrap metal, scrap aluminum, scrap steel, and then you just shine them down to a nice finish. And then that will allow for solar reflectors in almost any condition, because you can find scrap metal in most areas of the world, which is good, because solar reflectors, just like solar refractors, can be used for cooking, water purification, all those other things that can be problematic in some countries. Now, I'm going to do a little demonstration with this one just to show you that it's got a very similar kind of power. Anytime you're focusing the sun's light into a smaller confined space with the focus of the reflector or a refractor like the Fresnel lens, it's going to produce an increase in the heat from the thermal radiation, and you're going to get ignition. We've got some combustion at the focal point of the parabolic reflector now, and you can see a little bit of the smoke coming off. Combustion gases. Anytime you're burning a hydrocarbon-based material, like tissues, there will be smoke in the form of carbon dioxide, carbon monoxide, water vapor, and some stray carbons. Stray carbons are actually what causes soot. That's the black stuff there. So you can see that we do generate a lot of heat even with a very small reflective dish, which is really cool, because when you get a larger reflective dish, you can make enough heat for things like cooking or water purification, whatever else you need.